In 2008, the United States government ran a full simulation of a single earthquake. The result? 1,800 dead, 1,600 fires burning at once, a city of 10 million cut off from its water. The report runs over 300 pages. It is public. Anyone can read it. And the earthquake inside it has not happened yet. The fault it describes is real. It runs 800 miles through California. From the air, it looks like a scar that never healed. A straight, raked line drawn across mountains as if the landscape were two photographs laid edge to edge, slightly misaligned. Astronauts photograph it from orbit without magnification. On the ground, in places, it is nothing but a shallow trench in the dirt. You can stand with 1 foot on each side. The two sides are moving. The western side rides the Pacific Plate and carries Los Angeles northwest, about 2 inches every year. The eastern side carries the rest of North America. Between them, down to a depth of 10 miles, the rock is locked. A wall of stone ground into powder by past ruptures, pressed together, holding. 2 inches a year, every year, pressing against a lock. On the 9th of January, 1857, the lock broke. The ground tore open along 225 miles within minutes. The shaking lasted between 1 and 3 minutes, and it was felt from Sacramento to the Mexican border. On the Carrizo Plain, a dry stream bed was cut in half and its lower section shoved 30 feet sideways in a single motion. The Los Angeles River sloshed out of its bed. In the town of Fort Tejon, buildings dropped where they stood. Then the fault went quiet. That was 169 years ago. Farther south, the silence is older. The southern section of the San Andreas last ruptured around the year 1680, a date recovered not from any archive, but from the ground itself, from buried layers of broken earth that can be counted and dated like tree rings. Before the United States existed, before Los Angeles had a name. Since then, nothing. Not one great earthquake. 340 years of stillness on a boundary that has never once stopped moving. This architecture is not unique to California. Turkey sits on the North Anatolian Fault, the same type of boundary, the same behavior. It stayed quiet under the city of Izmit for generations, then broke in 1999 and killed more than 17,000 people in 45 seconds. New Zealand's Alpine Fault keeps the same rhythm, centuries of silence, then a rupture that shifts the landscape 30 feet at a stroke. Different continents, different rock, one mechanism. Long quiet, then payment. And here is the strange part. Seismologists have a name for a locked fault segment gone quiet too long. A seismic gap. And the southern San Andreas is the most documented seismic gap on the planet. It is measured, mapped, modeled, and remeasured every year. It fills the technical literature. It almost never makes the evening news. The comfortable explanation says earthquakes are random. Lightning strikes, nobody's schedule, nothing to be done. But the plates are not random. Their motion can be measured with survey markers and patience. 2 inches every year without exception for as long as anyone has been measuring. That energy has to go somewhere. If it is not being released, it is being stored. So the questions stack up. What exactly is stored beneath Southern California right now? And how do you measure a thing that hasn't moved in 3 centuries? Why does one stretch of this fault slide gently every day, splitting sidewalks by half an inch a year, while another stretch holds perfectly still?
Why did the one serious attempt to predict this fault fail in the most heavily instrumented small town on the planet? Who decided that a region holding one of the 5 largest economies on Earth could sit on the unpaid balance? And if silence is not peace, but storage, what does the withdrawal actually look like, minute by minute? You will see the withdrawal, hour by hour, from the government's own scenario, where the rupture starts, how fast it travels, what snaps in the first 2 minutes, and why the fires burn for days after the shaking stops. The scenario has a casualty count, a fire count, and a price tag accurate to the billion. The only thing it does not have is a date. At 12 minutes past 5 in the morning, on the 18th of April, 1906, the northern San Andreas broke loose. The rupture ran nearly 300 miles in well under 2 minutes.
In San Francisco, the shaking lasted about a minute. Ships far offshore reported striking something in open water, their captains convinced they had run onto rocks. The city is remembered for the fire that followed. 3 days of it. Most of San Francisco burned to the ground. But the evidence that mattered was not in the city. It was in the fences. Across Northern California, fence lines, roads, and rows of trees had been cut cleanly in two, and the halves no longer matched. Near Point Reyes, a country road was offset by 20 feet. The two pieces sat there in the morning light, parallel and useless. In Olema, a cow path ended at the fault and resumed 16 feet to the north. The offsets were greatest near the coast and shrank toward the ends of the rupture. A pattern, not a chaos, as if the displacement itself were obeying some rule that no one had yet written down. A dairy barn straddling the fault was pulled apart so precisely that its two halves remained standing, separated. Whatever had happened underground, the surface had recorded it like a ledger. The man who organized that ledger was Andrew Lawson, a geologist at the University of California. He had named the fault back in 1895 after a small valley called San Andreas, thinking he was describing a local feature of no particular consequence. After the earthquake, he led a state commission that traced the rupture mile by mile, photographed every torn fence, and published the findings in 1908, an atlas so thorough it is still cited today. The map showed a single continuous tear running most of the length of California. The local feature was the spine of the state. But the deeper discovery belonged to an engineer on that commission, Harry Fielding Reed. Reed did something nobody had thought to do.
He pulled the old land surveys of the region, 3 separate campaigns going back to 1851, and compared the positions of the brass benchmark discs that surveyors had cemented into the rock decades earlier. Cold, tarnished, unremarkable discs, each one a fixed point of reference, or so everyone assumed. They had not been fixed. Point by point, triangle by triangle, the comparison showed the land near the fault had been bending for half a century before the earthquake. Slowly, silently, a few feet over 50 years, like a bow being drawn by something patient. In 1910, Reed published the conclusion, and it remains the foundation of earthquake science. The crust behaves as a spring. The plates loaded continuously. The earthquake is not the event. The earthquake is the release. The event is the loading, and the loading never stops. I keep returning to one implication of that idea because everything in this story hangs on it.
If the crust is a spring and the loading rate is known, then a great fault is not a roll of the dice. It is a machine with a rhythm. Wind a spring at a fixed speed, and it must snap at something like fixed intervals. Reed himself saw it. He proposed that future earthquakes could be anticipated by surveying the slow bending of the ground. In 1910, that was a prophecy without instruments to fulfill it. It also raised a question geology could not yet answer. What is the rhythm of the San Andreas? Human records in California went back barely a century. One great earthquake in the north, one in the south, and silence around them. A rhythm cannot be read from 2 beats. The fault had been keeping time for thousands of years. Humans had been listening for 80. The full record existed.
It had been written layer by layer in a place nobody thought to look. The mud of a dry creek bed north of Los Angeles, where floodwater and marsh peat had been quietly filing the fault's history for 1,500 years. It would sit there, unread, for another 6 decades, until a graduate student named Carrie C. picked up a shovel. But before anyone could read the fault's past, science had to survive an embarrassment in its present. Because the San Andreas has one stretch that behaves like no other fault on Earth, a stretch where the earthquake machine appears to be broken. And for a while, that stretch convinced serious people that the danger might be an illusion. South of San Francisco, the town of Hollister is being torn in half, and nobody is alarmed. Sidewalk curbs step sideways an inch at a time, then get repaired, then step sideways again. House foundations crack along the same diagonal line, block after block, tracing the fault through living rooms and driveways.
A winery south of town was built directly on the trace in the 1850s. Its oldest wall has been splitting along the same crack for a century and a half. Repaired and resplit, the two halves of the building now offset by several feet. The ground here does not shake. It slides, smoothly, continuously, about an inch a year. This is the creeping section, roughly 90 miles of the central San Andreas, where the two plates slip past each other without storing energy. In the 2000s, scientists drilled a borehole 2 miles deep directly into this zone and pulled out the reason. The drilling took 3 summers. The bit crossed the active fault 2 miles down, and the cores it brought to the surface answered the question by touch alone. The rock was laced with talc and clay, soft, slippery minerals ground into a paste that lubricates the boundary. Fresh from the core barrel, the fault rock could be crushed between 2 fingers, greasy as soapstone. Steel casing installed through the zone bends measurably within months. The fault deforms industrial pipe the way it deforms curbs in Hollister, quietly and without pause. The spring cannot load because the spring cannot grip. For a while, this offered a comforting theory. Perhaps the whole fault leaked its energy this way, in creep, in swarms of small, harmless tremors, and the age of great ruptures was behind it. The measurements killed the comfort. North and south of the creeping section, survey lines and strain meters showed the opposite condition. Zero motion at the surface, full motion below. The segment that broke in 1857 had not slipped an inch since. The southern segment had not slipped in 3 centuries. Boreholes there found no talc, no lubricant, only hard rock, welded by pressure, gripping. The quiet sections were not leaking, they were locked. And the lock was exactly what made them lethal.
On the San Andreas, silence is not the absence of the machine. Silence is the machine, winding. At the boundary between the creeping section and the locked south sits a town of 18 buildings called Parkfield. Its water tower carries the town's entire identity in 3 words: Earthquake Capital, California. A sign at the cafe once read, "Be here when it happens." The joke was statistical. Parkfield had produced a moderate earthquake in 1857, in 1881, in 1901, in 1922, in 1934, and in 1966. 6 earthquakes of nearly identical size on the same patch of fault, spaced on average 22 years apart. The closest thing to a metronome ever observed on a major fault anywhere on Earth. In 1985, 2 government seismologists, William Bakun and Alan Lind, did something scientists almost never do. They published a formal, dated prediction in a scientific journal. The next Parkfield earthquake, they wrote, would arrive by 1993 with 95% confidence. The United States Geological Survey then wired the town like a patient in intensive care. Seismometers sealed in deep boreholes, listening below the noise of wind and traffic. Creep meters straddling the trace, sensitive to a hairline of motion. Strain gauges buried in rock, precise enough to register the ocean tide flexing the continent twice a day. Lasers swept the valley every night, measuring the distance between hillsides to a fraction of an inch. 70 years after Reed's prophecy, his experiment finally existed. If any earthquake on the planet was going to be caught in the act of beginning, it was this one. The instruments were installed. The town waited. The window opened. And the fault did something that no one, not the optimists, not the skeptics, not the authors of the prediction, had put money on.
To understand what, you first need to know what a shovel was finding at that same moment in the mud north of Los Angeles. Because while Parkfield tested whether the fault's future could be predicted, one man was discovering that its past could be read. And the past had a warning in it. In 1975, Kerry C. was a graduate student with a rented backhoe, a shovel, and a theory that senior colleagues told him was a waste of a career. His idea was simple. Where the San Andreas crosses a marsh or a creek, each great earthquake should leave a signature, a layer of ground broken by the rupture, then buried and sealed by the next season's flood silt. Dig a trench across the fault, and the wall of that trench becomes a book, each page a layer, each tear an earthquake. C chose a dry creek bed called Pallet Creek, 35 miles north of Los Angeles, and started digging.
The trench walls were cool and damp, and they were striped like cut cake, black bands of marsh peat, pale bands of flood sand, each boundary sharp enough to trace with a fingertip. And running up through the stripes, fractures. Layers snapped and offset by inches, then healed over by younger layers that lay across the break, flat and undisturbed. Each healed fracture was an earthquake. Each band of peat carried its own radiocarbon date. C spent 3 years on his knees in that trench, with a trowel and a magnifying lens, tagging every layer, bagging every sample. He was not theorizing about the fault's history anymore. He was standing inside it, reading it by lamplight. The book contained 10 great earthquakes in roughly 1,500 years. When C published the record in 1978, it was the longest earthquake history ever recovered for any fault on Earth. The average interval between ruptures? About 135 years. The last entry in the book was 1857, the rupture that threw the fences of the Carrizo Plain 30 feet. The counter, today, stands at 169. But the average concealed something worse. The intervals were not regular. The earthquakes came in clusters, gaps as short as 50 years, then lulls stretching past 2 centuries. Reed's machine was real, but its metronome was loose. The rhythm existed, and the rhythm could not be trusted for scheduling. A fault could run early, a fault could run late. And to the south, beyond the reach of the 1857 rupture, one section was running very late indeed. No rupture since roughly 1680. Take 340 years of silence, multiply by the measured loading rate, and the arithmetic says more than 20 feet of motion is currently stored in the rock beneath the Coachella Valley, cocked and waiting on a trigger no instrument can see.
Which brings us back to Parkfield, the metronome town where the formal prediction window was closing. 1993 arrived. No earthquake. The window shut. The years piled up, 5, then 10. Congress asked pointed questions about the program's budget. Some instruments were maintained, some careers quietly moved on. Then, on the 28th of September, 2004, 11 years past the deadline, the Parkfield earthquake finally struck. Magnitude 6, almost exactly where predicted, almost exactly the expected size. Hopelessly late. The most heavily monitored patch of fault in existence had just produced its long-awaited earthquake directly beneath the sensors, and every recording survived. Scientists tore into the data looking for the beginning, the precursor, the tell, the whisper before the break. The strain meters had caught nothing, the creep meters, nothing.
The borehole seismometers registered no warning of any kind until the rupture itself was already running. Between loaded and breaking, there had been no measurable transition at all. The fault had simply let go. I want to be precise about what died at Parkfield, because it was not hope. It was a specific kind of hope. The fault's past can be read. C proved it in the trenches. The fault's stored balance can be measured. The surveys prove it every year. What cannot be known is the date. There is no countdown to intercept, no signal to catch, no final warning between silence and rupture, which leaves only one honest forecast for the southern San Andreas, and it is the one nobody wants. Not when, only how big, and what breaks. In 2008, the United States Geological Survey decided to answer that question properly. They gathered 300 scientists and engineers, and they built the earthquake in advance. The scenario is called Shakeout. Its lead author was Lucy Jones, the seismologist who had spent 2 decades as the public face of earthquake science in Southern California, the calm voice explaining every tremor on live television at 3 in the morning. Her team of 300 did not model an unusual earthquake. They modeled an ordinary one, magnitude 7.8, the size the southern San Andreas has produced over and over through the layers of sea's trenches. Then they followed the consequences through every system a modern city depends on, pipe by pipe, road by road, hour by hour. What follows is their document. The rupture begins at the fault's southern tip near the Salton Sea, 10 miles down. It unzips toward the northwest at nearly 2 miles per second, faster than sound travels through air. In under 2 minutes, 200 miles of fault tear open, the ground on one side lurching as much as 20 feet past the other.
The rupture passes San Bernardino, where the fault runs directly beneath neighborhoods, and drives its energy into the Los Angeles basin, a bowl of soft sediment that traps seismic waves and makes them ring like water sloshing in a bathtub. In parts of the basin, the strong shaking lasts nearly a minute. Witnesses to earthquakes of this size always describe the sound first, a roar out of the ground, like a freight train arriving from below, and then the sight that no one is prepared for, solid earth moving in visible waves. In those first 2 minutes, the scenario severs the region's arteries. Every major freeway crossing the fault is cut, bridges down, roadbeds offset by feet. Fiber optic trunk lines, gas mains, and high-voltage corridors cross the same rupture zone, and they fail in the same 120 seconds. And then there is the detail that outweighs the rest of the document. Los Angeles imports nearly 90% of its water. The 3 great aqueduct systems that carry it, from the Owens Valley, from Northern California, from the Colorado River, all cross the San Andreas Fault. All 3. In the scenario, all of them are severed in the first 2 minutes, and the repair estimates are measured not in weeks, but in months. The reservoirs inside the city hold roughly 6 months of supply. The clock on that supply starts at the 2-minute mark. The fires begin within the hour. Ruptured gas lines, arcing wires, overturned equipment. 1,600 separate ignitions across the region. On an ordinary day, any one of them is a manageable emergency. In the scenario, they arrive simultaneously, on broken roads, to fire crews connecting hoses to hydrants fed by shattered mains. The document is written in dry, procedural language, and it delivers its worst line without raising its voice. Many of the hydrants are dry. Small fires merge into large ones. The burning continues for days, and in the final accounting, the fire damage rivals the shaking damage. The same sequence that destroyed San Francisco in 1906, replayed across a region of 20 million. The ledger at the end of the document: about 1,800 dead, 50,000 injured, $213 billion. Months without full water service in the second largest city in the country. Aftershocks in the magnitude 7 range striking during the repairs. But the number that unsettles the planners most is none of these. It is the recovery time. An economy that cannot restore water, freight, and power within weeks does not pause and wait. It relocates, and some of it never comes back. The scenario was released in 2008, and millions of Californians now drill against it every year, the largest earthquake drill in the country's history. But the drills rehearse the first minute, the shaking, the shelter. The document itself is mostly about everything after: the dry hydrants, the cut aqueducts, the long arithmetic of repair. That part cannot be rehearsed. It can only be paid. One question remains, and it is the one the scenario deliberately left out. Shakeout modeled the southern fault breaking alone, its rupture stopping short of the mountains east of Los Angeles. The trench record and the satellite record suggest a darker possibility, that the sections do not always break alone. Everything in this story now converges on a single stretch of ground east of Los Angeles. Reed supplied the mechanism. The crust is a spring, loaded at a fixed and measurable rate. C supplied the record. The southern San Andreas fires roughly every century and a half, and it has been silent for more than 3. The surveys supply the balance. over 20 feet of stored slip.
What remained unproven for decades was the present tense, hard evidence that the storage is still accumulating, that the Southern Fault is not secretly leaking its energy the way Hollister does, an inch at a time below the threshold of attention. In 2006, a geophysicist named Yuri Fialko closed that gap. Fialko stacked 8 years of satellite radar images of Southern California, a technique that compares the ground's position from orbit, pass after pass, and detects movement of a fraction of an inch across thousands of square miles. The picture that emerged showed the land on either side of the southern San Andreas warping at the full plate rate. The bow is still drawing. Nothing is escaping. His conclusion, published in the journal Nature, was as close to a warning as the technical literature permits. The southern section has accumulated enough strain to produce its next great earthquake, and it may be, in his phrase, past due.
The ground itself communicates the same conclusion in a cruder language. In the Coachella Valley, where the stored energy is oldest, summer air temperature exceeds 110 degrees. The fault trace runs as a low, sun-hardened scarp you can follow on foot for miles, through date farms, past golf courses, under power lines. A 3-century-old pressure ridge that has never once moved in the lifetime of the nation built on top of it. 500,000 people now live in that valley, directly on the loaded section. But the true unknown is not the southern section. It is the junction. At San Gorgonio Pass, east of San Bernardino, the San Andreas stops being a clean line. The fault bends nearly 30 degrees, splinters into overlapping strands, and dives at conflicting angles beneath some of the steepest terrain in Southern California, a mountain front rising 10,000 feet directly out of the desert floor. Through that same pass, in a corridor barely a mile wide, run Interstate 10, the main freight rail line to the eastern half of the country, the Colorado River Aqueduct, and a bundle of gas and power lines, the desert lifelines of Southern California, threaded directly through the fault's most tangled geometry. Geologists call it a structural knot, and it poses the question that determines the size of the future. Does the knot act as a barrier that stops a southern rupture, or, once every few centuries, as a gate that lets one through? The trenches suggest the gate exists. Paleoseismologists have since dug dozens of sites along the Southern Fault, extending C's method down the entire system. Around the year 1680, and again in earlier layers, the dated ruptures on opposite sides of the pass line up, hints that the southern and central sections have, at times, broken together or in rapid succession as a single event.
A rupture that threads the knot does not add its segments, it multiplies its energy. The shakeout scenario at magnitude 7.8 assumed the gate stays shut. The record in the mud makes no such promise. This is the full shape of the situation, stated plainly. One of the 5 largest economies on Earth is built directly across a locked plate boundary. The boundary is loaded to the level at which it has historically always fired. The loading has been verified from orbit to a fraction of an inch. The firing interval is overdue at the fault center, and 3 times past due at its southern end. There is no precursor to detect and no countdown to intercept. Parkfield settled that permanently. And the one geometric feature that decides between a regional catastrophe and something larger is a knot of shattered rock 2 miles down that keeps its intentions to itself.
Carrie C's trenches at Pallet Creek have since been re-excavated and extended by 2 generations of scientists, checked and redated with methods that did not exist in 1975. The walls still show the same 10 dark, healed fractures, stacked like closed accounts. Above them, at the very top, sits the layer being deposited right now, soft, sunlit, unbroken, waiting for its entry. Geology does not threaten. It accumulates. Somewhere beneath the Coachella Valley, tonight, the 2 sides of the San Andreas will move a fraction of a millimeter closer to a number nobody knows. The same fraction they moved last night, and the night the scenario was published, and the night Reed compared his surveys, and every night of the 340 years before that.
The fault is not waiting in any sense a human would recognize. Waiting implies attention. This is bookkeeping. Patient, exact, and utterly indifferent to what has been built on top of the ledger.
The ledger has been balanced before, 10 times in the walls at Pallet Creek. Each of those 10 earthquakes struck a landscape where the silence had lasted longer than anyone's memory, which is the only condition silence needs to be mistaken for safety. The people of 1857 had no reason to expect the ground to move. It never had in their lifetimes, or in the memory of anyone they had ever met. The absence of experience felt like evidence. It was only an interval. The modern version of that feeling is more sophisticated, but it is the same feeling. The freeway has always reopened. The water has always flowed. Every earthquake in living memory, even the ones remembered as disasters, the ones with their own documentaries, has been, by the standard of the trench record, minor. Partial releases on secondary faults, 10 or 20 seconds of shaking, single neighborhoods rebuilt.
Southern California has never, in its entire existence as a modern society, experienced its own fault. Everything it knows about earthquakes, it learned from the understudies. The main performer has not been on stage since before the nation existed. None of this is a reconstruction of some distant epoch. The loading is being recorded in real time. Several hundred survey stations stand across California today, cemented into bedrock, taking their positions from satellites every few seconds, the direct descendants of Reed's brass discs, doing automatically what he did once with 50 years of paper. Their data is public and updated continuously. Anyone can watch the two sides of the state slide past each other week by week at the speed fingernails grow. The bow drawing back is not a metaphor from a textbook. It is a measurement with a timestamp from this morning. What separates this catastrophe from nearly every other in history is that it has been fully described in advance.
The mechanism is understood, published in 1910. The rhythm is counted, published in 1978. The stored energy is measured from orbit, published in 2006. The consequences are itemized to the dollar, published in 2008. 4 documents spanning a century written by people who never met, converging on one event. Civilizations are usually granted hindsight. The warnings are found afterward in hearings and inquests, and the story becomes who ignored what. This one has been granted foresight in writing with a century of lead time. The record will show what was done with it, which pipes were hardened, which crossings were rebuilt, which aqueducts were rerouted, which pages were read, and which were filed. I don't know when the southern San Andreas will break, and neither does anyone else. That is the one fact Parkfield made permanent. But I keep thinking about the top of that trench wall.
Every layer in it was once the present, soft, sunlit, unbroken, the quiet surface of somebody's ordinary decade. The people who walked on it assumed, correctly, that tomorrow would resemble today. Right up until the morning the fault balanced its books, the flood silt came down, and the present became an entry in the record. One more dark fracture, dated and filed, indistinguishable from the others except that, for the people standing on it, it had briefly been everything. The layer forming now is already thicker than most of the intervals below it. The arithmetic that fills this film runs through it just the same. 2 inches a year, 20+ feet in storage, a rhythm overdue, a knot that decides the magnitude. A scenario with every number printed except one. The question the San Andreas leaves is not whether the next entry gets made. 10 healed fractures already answer that. The question is quieter, and it belongs to everyone living on the soft layer at the top. When the missing date is finally written in, will the record say this was the civilization that read its own forecast in time, or just the 11th line in the mud?